Hi, welcome. In this video, we will solve problem lowest common ancestor of BST binary search tree asked by companies like Amazon, Spotify, LinkedIn, Oracle, and many others. Now let's solve a bit more good level problems on binary trees. Okay, so let's check out this problem lowest common ancestor of a binary search tree. So given a binary search tree, find the lowest common ancestor node of two given nodes in the binary search tree. Okay. So what is the lowest common ancestor? Basically, the lowest common ancestor of two nodes, suppose P and Q, will be the lowest T that has both P and Q as descendant. Okay, let me explain you. So suppose this is one node P, right? This is one node Q, right? 2 and 8. So the lowest common ancestor will be, of this node will be T that both P and Q has descendant. So for this is the descendant, right? And there is no further root ahead. For this is the descendant. There is no further root ahead. And this is the common, right? This is the common. This is the first common, right? If I say this is the first common starting from bottom, first common, let me write it clearly. Is first common from bottom. So that will be the lowest common ancestor, LCA. Okay. Let's suppose instead of this P and Q, suppose you have let's suppose you have this P and this Q, right? 0 node is P, this is 5 is Q. Okay. So this is your root node. So one path from P to the root node will be this path, right? This path, and these will be the all ancestors basically, right? Because the node is also an ancestor of itself, right? So this node, then this node, it's the parent node and more parent, okay, ancestor. For this queue, this will be the path of ancestors, right? This will be the path. So where they have the first common from the bottom, right? This two is the first common from the bottom. So this will be the ancestor of them, right? Because from there, here they are separating. Basically, you can see, right? My parents, then their parents, right? My parents, then their parents, then their parents. So if I find out a connection, right, of my cousins, right, I will get some here, my grandfather, then right, something like this. Exactly like it's same here, right? This is the suppose grandfather. Grandfather has one children, and from one children they got 1 0, and then again one children, and from there they got this thing. So what is the common first parent, right? This is the common first ancestor. Okay. Similarly, if you take an example of, suppose, if you take here 3 and 5, right? P is Q, P is 3 and 5 is Q, right? So which will be the common here? This will be the path of ancestors for P, right? And for Q, this will be the path for the ancestors. Right? So which is the first common? Fourth is the first common, right? So I hope this is clear to you that what is lowest common ancestor, right? How to find a lowest common ancestor. Okay. Now let's see how we can solve this problem. So let me again draw the figure that we have first 6, then 2, then we have 8, okay, then we have 0, then 4, here we have 7 and 9, then we have 3 and 5, right? Now the things are clear to you, okay? How to find a lowest common ancestor. Okay. Now suppose let's take one more example. Suppose 4 is P, right? This node, fourth node is P, and this is Q. Then what will be the common ancestor, right? So let's take the complete path of P and complete path of Q, and here they are intersecting, right? So yeah, fourth node itself, right? Fourth node itself will be the ancestor, right? So basically, where they are intersecting, you just need to check this one. So here, this will be this case. Now let's see. if you can see binary tree, this is not a binary tree. Okay, this is a binary search tree. Binary search tree, not binary tree. So what is the difference between binary search tree and tree? Basically here you can see this is a search tree, so this is already sorted, right? This is not a random as binary tree. So basically you can see here in binary search tree, we have this as a root node. Okay, in binary search tree, in the left there will be like the nodes, those have decreased value from the root, and in the right side, right on the right node, they have the values that are increased values. So nodes those who have increased value on the right side, nodes those who have in decreased value in the left side will be come under the binary search tree. You can see, right, we have 6, right? Now 2 is a decreased value, right? 2 is lesser than 6, so it will come here. Then 8 is greater than 6, it will come here. And further ahead, right? Because on all the subtrees, right? Further ahead, 7 is lesser than 8, so it will come on the left. 9 is greater than 8, so it will come on the right. Right? 0 is lesser than 2, so it will come on the left. 4 is greater than 2, so it will come on the right. Now from 4, 3 is lesser than 4, it will come on the left. 5 is greater than 4, so it will come on the right. Right. So basically on a particular node value, okay, okay, on left there will be a lesser node value. Suppose x is lesser than node value, and here x will be greater than node value, and this is applicable to all the subtrees, right? Able to all subtrees. Okay. Now let's see how we are going to solve this problem. Okay. And see the, like, if I talk about the first approach, that will be a brute force approach, that simply checked out the root, again call the left node, then right node, and go ahead, call the left node and right node, and then find the common ancestor, right? Simply find out when there is a common link between these nodes, right? But here we have a binary search tree, that's a different from the binary trees, right? You can see in the right direction from a particular node, the values are increased, right? The values are increased. Here the values are decreased, right? On each particular node, right? Here the value will be decreased, the value will be increased, right? Here as well, right? So can I take a help from this binary search tree? Okay, can I reduce my time complexity and space complexity if I basically considering from binary trees? So yes, we need to think a bit more smarter, okay, because we have provided with binary search tree. If we will do the same thing that we do in the binary trees, then there is no sense. So what I will do, right? See what are the things that you are getting here. You have p equals to 2, okay, and you have q equals to 4. Okay. Now let's take one example of p that, let's take your p is here, right? This zeroth node, and q is here at the 5. So P is at 0 and Q is at 5. Okay, and the common ancestor will be 2. Alright. So now we will check from the root node. Okay, that is 6. Okay, let me remove this. So we have 6 here. From 6 got 2. From 2 this was 2. See what I will do, I will check for 6, right? That is 6 node value. Okay, node value basically. So I am checking with the node value. Okay. Now I will check P and Q both are P and Q both are lesser than 6. So there is a high or extremely very high probability that both the nodes will be lie here on the left side. Right? Both the nodes lie here on the left side. Completely true. Right? Right? 100% they will lie on the left side because the values are lesser than that. If the values are greater than, then it will lie on the right side, but the values are lesser than it, so it will lie on the left side only. What I will do, from here I am getting an instruction, right? Previously what I was doing, that like on a binary trees, what we were doing, like you need to call left node, right? And right node, basically, no matter what it is. But here we can take an action, right? When we need to take left or right, it's like you are getting a correct direction that you don't need to, you don't need to follow all the paths. No, you will take only the right path, and here the right path will be left node because the values are lesser. Okay. Now you will come to at 2. Okay. And from 2, you are getting that is 1p is smaller than 2. That means it will lie somehow here, right, on the left side. But 5 is greater than 2, that it will lie on the right side. So when there is a divergent from any given node, right, that one node p will be lie here, q node will be lie here. Whenever there is a divergent, can I say that that node itself will be the ancestor, lowest common ancestor? Because we are getting a divergent from that node. And yeah, that will be the answer. Whenever you are getting a divergent from any node, that one p will be lie, like one node will be lie on the left side, one q will be lie on the right side. You can say that from that node, that's a lowest common ancestor. Let's check out one more example. Suppose we have p equals to 3 here and q equals to 5. Okay, and let's start the same thing. Let's start the same thing from here. So p is 3 and q is 5. So I will simply check 6, right? And I will check, is p is lesser than 6? Yes. And q is also lesser than 6. That means they will lie on the left side. Yes. So I will come to the left node. Okay. Once I come to the left node, again I will check, is p is lesser than 2? No, p is greater than 2. And 5 is lesser than 2? No, 5 is also greater than 2. So both are greater. That means they will lie on the right side. Okay. From 2, like 3 is also greater than 2. You can see p is also greater than 2 and q is also greater than 2. Both are greater. So they will lie on the right side. So I will call the right, right node. Now once I call the right node, I will check with 4. Is p is greater than 4? No, it's lesser. So here p is lesser than 4 and q is greater than 4. So again, there is a like one is greater, one is lesser. So there is a divergent. So can I say my 4 will be the lowest common ancestor? And yes, 4 will be the lowest common ancestor, right? So let's now understand the cases, right? See, if I simply move all these things a little bit here. So see, what are the cases we are getting? If p is lesser than our root.val and q is also lesser than root.val, both are lesser. Okay. Can I directly say that I need to call the left node? I will call the left node, right? Next case is, suppose p is greater than root.val and q is greater than root.val. Both are greater. Then no doubts, I need to call a right node only. Now when there is a difference, that means two cases here, that p I can greater than root.val and q can be lesser than root.val, or one case can be p lesser than root.val and q greater than root.val. That means opposite. One is greater, one is smaller. In these cases, right, can I directly say the node itself is the lowest common ancestor? I will directly return node. So here I will return node. Okay. Now let's explore this one case also. Okay. One case when we have P and Q on the same line, right? Right. So what I will do here, we have P equals to 9 and Q equals to 8. So what I will do, I will again check, right? Is P is greater than 9? P is greater than the root node, that is 6. Yes. Q is also greater than. So I will call the right one, right? From right, I will check, is P is greater than? So yes, P is greater than the root node and Q is greater. No, Q is equal. In that case, whenever I am getting any node equal, In that case, that will be an LCA. So if I add one more condition here, let me move this little bit upward. And this will be about lowest common ancestor. I'm adding one more condition here. That it's not about whenever they are opposite. It also when suppose P is equals to root dot well and Q suppose and Q is not equal. Suppose Q is not equal to root dot well. In that case also the node itself, the same case. In that case also the node itself will be an LCA. Similarly for Q, right? I am not writing here that basically Q is equals to root dot well and P is not equals to root dot well. In that case also it will be the node itself. So basically now you can see, let me now create a new diagram here. So suppose this is my 6 and here we have 2, here we have 8 and here we have 0, here we have 4, 7, 9. Right. So, right, only in the two cases, right? One case where both P and Q, right, both P and Q are lesser than the value. So let me write it here. P and Q both are lesser than the suppose root dot well. Both are lesser. What I need to do? Both are lesser, like P and Q both are lesser. I need to call left node. Okay, second case condition, if P and Q both are greater than root dot well, then I will call right node. Okay, the third case, right? Or can I come to the third case that all the other cases? Can I say that all the other cases, in all the other cases, what I need to do? I need to return the node itself. All the other cases. Yes, what are these cases? So worst case can be that your P is greater than, let me say root dot well as RV. Okay. So is suppose P is greater than root value and Q is lesser than root value. That is one case. One case can be Q is greater than root value and P is lesser than root value. Right. One case can be P is equals to root value and Q is suppose lesser or greater, that is not equals to root value. Okay. Or Q is equals to root value and P is not equals to root value. Right. So these will be the all other cases. All other cases. In all these cases, I need to return node. I need to return node only. Okay, whenever I am getting divergent like 0 and 4. So 0 is lesser, 4 is greater. So I am getting a divergent. So this will be my node, this lowest common ancestor. Okay, and whenever I am getting same, so suppose 2 and 4, where 2 is equals to my node that I am calling and 4 is less, 4 is greater than, right? Then also I will have lowest common ancestor as 2 only, right? So yeah, this is how we are going to solve this problem. And now we can solve this problem very easily, right? We know when we need to take right step and when we need to take the left step. And whenever there is a difference, I will simply return the root. Okay. Let me write the pseudo code of it. What will the pseudo code here? Let me write it here so that you can also check with the conditions. So what will the pseudo code? Let me use green pen here. Okay. So LCA, basically you will call your root node with value P and Q. Now in LCA, you will suppose whenever you are getting a root node equals to null, what you will do, you will simply return. Okay. So let me write one thing. Whenever we are getting a root node equals to null, we will simply return from this function, right? We can return null, right? Suppose you are coming to here null, you will simply return, right? Suppose you are coming to here null, you will simply return. Okay. Now the case is if suppose P, because the P and Q are nodes, right? So p dot value is lesser than root dot value, and q dot value is also lesser than root dot value. Okay, when both are lesser. So what I will do, I will call LCA with both are lesser, that means root dot left, and I will call P and Q. Now the next case, if P dot well greater than root dot well and Q dot well is also greater than root dot well, when both are greater, then I will call LCA with root dot right. Okay, and with P and Q, right? In all the other cases, what I am doing, I am returning the node itself. So here I will say simply return the node itself. Okay, so return what is node? Node is basically root. So I will return a root. And yeah, this is how you can solve this problem. Okay, so yeah, that's a complete done this pseudo code. In the next video, I will show you a quick code implementation that will be same exactly like the pseudo code. And then in the next video, we will do a quick dry run that how it is working. Okay. So yeah, that's all for this video. See you in the next video.